I want you to just go ahead, take your time, read through it. If you got questions, you guys know how to get a hold of me. It's no issues. We're going to skim through certain things, then go in depth with others. So we're really just talking about the function of our cardiovascular system, which is made up of three major components. The pump, which is the heart, the fluid, which is your blood, and then the pipes, which is your vascular system. So that's your aorta, arteries, arterioles, capillaries, venules, veins, and then vena cava. Now, obviously, how this is going to respond to exercise in the acute sense, and then how it is going to adapt over the long haul. So what's going to go on as far as increasing our ability to deal with this stress acutely, delivering nutrients and removing wastes, and then effectively how we're going to be able to control, or we control this through a number of different feedback mechanisms in the body. So it delivers oxygen, delivers glucose, delivers amino acids, vitamins, minerals, cholesterol, fatty acids to our cells. It removes actually some cholesterol, that's the difference between HDL and LDL, removes carbon dioxide, removes ammonia or urea, which will eventually pass in our urine, or nitrogen effectively. And it's also going to help remove, or at least allow us to transport around lactate, which can be used as fuel. And this is also, we're going to move around hormones. It's going to help maintain our body temperature and also maintain our fluid compartments throughout the body. And it's obviously going to help with disease prevention, because that's the major highway that our immune cells are going when they're flowing through our body, so we can have those immune response where we need to have them. So the pump is the heart. Blood comes in through our vena cava, goes into the right atria, it's going to go into our right ventricle via the tricuspid valve, then gets pumped out of there through the pulmonary valve into the pulmonary artery, which then leads through the lungs, comes back to the pulmonary veins, goes into the left atria, goes through the bicuspid, aka mitral valve, into the left ventricle, and then from the left ventricle is going to be pumped through our aortic valve out into the rest of the body. So the other little thing to make sure you guys understand is we have what's known as these chordae tendineae and these papillary muscles that they effectively are, it's working as kind of almost like the parachute lines in the muscles that are keeping our valves functioning like they should. So that way they're going to obviously open and close appropriately, depending on where we're at in our wonderful contraction relaxation cycle. So the myocardium, that's the actual muscle. This is going to be thick depending on how much pressure happens to occur in that chamber. So chambers that have to deal with higher pressures are going to be thicker. So your left ventricle is actually going to be the thickest chamber, because that's the one that pumps the blood to the rest of your body. And with exercise, specifically more with aerobic exercise, we're going to increase the size of the actual filling part of the ventricle, so its capacity, and we're going to increase the myocardium a little bit, the muscle a little bit thicker. Now, if we're doing a lot of power training, so a lot of Valsalva, high pressure, we're going to be increasing the myocardial thickness, but not really increasing the size of the chamber as much. And one thing to be careful of is some folks, thanks to, unfortunately, some genetic defects, they are going to find that they have this thickening of the myocardium in what's known as eccentric hypertrophy is the positive one that happens with aerobic training. Concentric hypertrophy is what happens when the muscle gets thicker and the actual capacitance decreases, and because of that, this is what sometimes leads to sudden athlete death. Now, a key difference between myocardium and skeletal muscle is what's known as intercalated discs. These are literally what allows an action potential to travel from one cardiac muscle fiber to the next. This is a good thing with cardiac muscle fiber because it's going to allow that signal to jump across and jump across and jump across. So your entire heart contracts and relaxes each time, as opposed when we talk about skeletal muscle, when we're just going to get a couple fibers to turn on, a couple more fibers to turn on, and eventually we can turn on all those fibers and get maximal force production in a graded sense. Because if that the same way our muscles worked, we'd have to contract our muscle fully and relax it fully each time. So our conduction is going to occur starting off through what's known as the SA node, the sinoatrial node. It's going to depolarize thanks to pacemaker potentials, which occur thanks to what's known as leaky channels. This is going to then go across the Bachmann bundles, which go in left atria, from the right atria to left atria. That's going to go through the myocardium of our atrias, and then it's going to eventually get to our atrioventricular node, or AV node. From there, it's going to go into our AV bundle, sometimes referred to as the bundle or to the AV bundle, or the bundle of His. And then it's going to go down our individual bundle branches into the Purkinje fibers, where it's going to widen out, and then it's going to go into all of the myocardium of our ventricles. The advantage of going from the bundle to the branches to the Purkinje fibers is nerves conduct faster, so it allows the action potential to be touching a lot more muscle at the same time, as opposed to if it had to jump from one muscle to the next all the way around the heart, you wouldn't have as well controlled of a contraction. So we have some extrinsic control of our heart, our parasympathetic nervous system. So remember, guys, that's going to be the rest and digest is going to be through the vagal nerve, which is going to decrease our heart rate and the force of contraction. This is what's functioning when we happen to be at rest, which is slowing down our heart rate. It's a good thing. If you completely had an uninnervated heart, your resting heartbeat would be about 100 beats per minute. It actually happens in individuals who've had a heart transplant. Sympathetic nervous system, aka epinephrine, norepinephrine, or sometimes you guys hear as adrenaline, noradrenaline, that's what's going to be released that's going to increase our heart rate. And this is a good thing because that's what we're going to release when we're exercising to go ahead and get our cardiac output up higher. So we're going to be able to deliver more blood, which is going to deliver more oxygen and allow us to exercise at a higher intensity. So here's the example of when someone has greater amounts of vagal tone. So you can actually see how these individual depolarizations get further and further apart, as opposed to when we talk about putting in epinephrine and you see how they get closer and closer and closer. And that's the natural effect of obviously getting that contraction to occur at a higher rate. So now what's known as a pacemaker potential, it's where these leaky channels are going to cause these structures of the heart to naturally depolarize. The SA node happens to do this at the fastest rate. Now the next fastest rate is typically coming from the atria themselves, then from the AV node, and then Purkinje fibers and the ventricles. So this is why sometimes your heart will skip a beat or go a little bit faster. But the key is whichever one depolarizes first causes everything else to depolarize. So if your SA node fails, then you're going to run off your atria randomly depolarizing. If your atria fails, then you're going to run off your AV node naturally depolarizing. And if the AV node fails, then we're down the Purkinje fibers, and that is a very, very, very low heart rate. So blood flow to the heart should be something that is pretty understood for you guys. Your atria are going to contract first, which is going to cause our ventricles to be completely topped off. Now, the ventricles would have already been filling even when the atria were not contracting, when the ventricles are relaxing. The key is we get a little topping off of blood whenever they're going to contract. And then once the ventricles contract, it's going to close the valves going back to the atria and open the valves going into the pulmonary arteries and the aorta. And that's where we're going to actually get blood pumped around the heart. So the ventricles are the things that really, really matter. Now, there's a variety of potential cardiac arrhythmias that people can have, one of which is called bradycardia, and this is when your heart rate is simply going to be lower than 60 beats per minute. If this happens because you're an athlete, because you're in shape, that's not a bad thing. That's actually a good thing. Then there's tachycardia. This is going to be your resting heart rate is above 100 beats per minute. So your heart rate is beating faster than it should. If we're exercising, that's fine. But if you're just laying around with resting tachycardia, that's a bad sign. That's something where you should probably get checked out, go see a cardiologist because things are running faster than they should be. Premature ventricular contractions. This is going to be like where you feel like your heart kind of skipped a beat or has gone a little bit faster. This is something that can occur. If it happens more frequently, it's worth going to a cardiologist. And then we have what's known as ventricular tachycardia, which is where you have a number of these premature ventricular contractions that, if it's not taken care of, could lead to ventricular fibrillation. And then this is what's literally going to cause your ventricles to contract in a completely uncoordinated fashion, which literally can lead to death. So bad. Now, the way that we're going to actually look at this electrical signal inside of the heart is via what's known as an electrocardiogram. This literally looks at the electrical activity of the heart and what's going on and changing. The first bit of depolarization is occurring in the atria. This is what's known as the P wave. There then is a flat segment, the essentially PR segment, where it's going to be just a flat baseline. This is going to be where the signal is going from the AV node through the AV bundle, through the bundle branches, through the Purkinje fibers, and then we get to the QRS complex. This is where our ventricles are going to depolarize, and inside of this, the atria is also repolarizing. It just happens to be so small by comparison you can't see it. And then we have our T wave, which is going to be where we're going to have our ventricles repolarizing, which was once again after a nice little flat segment. So it's going to look like this. So questions so far, Yeho or Jabari, for anything we've talked about?
I have a question, Dr. Lane. Sorry, I don't have the video on. I'm just in the middle of something. But so when is it true? I've heard, and I think it is true, but I just want to double check. So if the heart is not receiving any impulses, it can still generate action potential, right, within itself.
Yeah,
right?
That's the entire point of what's known as the pacemaker potentials.
Okay, that's okay.
Yeah, in the SA node, there happens to be literally, is referred to as a leaky channel.
Okay, that's what yeah, you were describing that. Okay.
Naturally allows sodium to leak into the cardiac muscle fibers there until eventually it causes it to get to its own threshold, which is then going to open those voltage gated channels, just like a normal muscle contraction. And then that's going to cause an action potential to be generated. Now that action potential that's generated is going to jump thanks to those intercalated discs from one cardiac muscle fiber to the next. So that's why the heart is autorhythmic. Hence, when someone has a heart transplant, that heart's going to be on its own. Like you don't do anything to it. The key is now, since they don't have vagal nerve, they don't have vagal tone to that heart is naturally going to have a much higher resting heart rate because it's not having anything to tell it to go slower.
Mm-hmm. So does that mean that when that individual with the heart transplant exercises, the regulation of that would be different because there's nothing that connects pretty much from central nervous system to the heart, right?
But the only thing that's connecting to that heart through the nervous system is the parasympathetic nervous system. You still have sympathetic nervous system tone because obviously epinephrine is dumped in your blood, and that's what goes to the heart.
Okay.
So they're still going to be able to have good exercise response. The key is the relaxation response. Their heart rate's going to be a lot higher than you think, just because of that.
Okay, thank you.
No, man, good question. Good question. As we have a gold star attendance day for lecture. So whenever we're talking about the cardiac cycle, this is going to be all the way from that P wave all the way to that T wave. So whenever we're relaxing, that's going to be from the T wave to the next QRX complex, because in between that time, no blood is being pumped out of the ventricle. From the QRS complex all the way to the T wave is where we're going to have systole. And this is where our heart is going to be contracting, so blood is going to be being pumped out of the heart. So hence diastolic blood pressure, that's the diastole when the heart's relaxing. The systolic blood pressure, that happens to be whenever the heart is in systole, which is contraction. So everything that's occurring, guys, here as far as with the heartbeat is going to be between relaxation and contraction. So this right here is part of what's known as the Wiggers diagram. If you understand the Wiggers diagram, you've got a really good understanding of what's going on as far as in the cardiac cycle. So specifically what's highlighted here, guys, you can see how the lowest blood pressure right here, and this is the aorta, because that's really what we're measuring peripherally, because technically the pressure inside of the ventricle, whenever we're really relaxing, it's going to be zero at certain points, because it's going to be completely passive and just letting itself be filled. Now, once it starts contracting, as soon as it overcomes our lowest or diastolic blood pressure, heart or blood is going to be being pumped out of the heart. And that's going to continue for as long as until that pressure comes back down and is below effectively the aortic pressure. And then that's, again, no more blood is going to be leaving the heart. So you can kind of see, and Yeho, do you have your slides up yet, or are you still figuring that out?
I'm kind of...
You're kind of going in and out, bud, so it's okay. It's okay. You'll be able to look up the slides later and otherwise, but obviously right now, Jabari, you can see what I'm talking about, where you can actually see, yeah, this period in time when there's contraction, and then the rest of the time whenever we happen to be in relaxation, because it's all about overcoming the aortic pressure. So the atrias are going to receive the blood into the heart. Left ventricles are going to then pump it to go to the rest of the body. Left ventricle is thicker because that's where we need more strength so we can overcome the pressure in the aorta. And that's going to obviously hypertrophy based upon how much training and the types of training we're making it go through. We have the heart has its own conductive system that's going to cause it to depolarize. It is slightly linked to our nervous system, but not as much as one would think in a traditional sense. We're going to have the pacemaker of the heart be the SA node when it's in a normal, healthy situation. Our autonomic nervous system via the parasympathetic nervous system and vagal tone is going to decrease our heart rate. Through epinephrine and the sympathetic nervous system, it's going to increase heart rate, and EKGs are going to tell us what's going on. So, well, I don't know what I'm doing right now, but I'm going to stop it. Now, the concept of stroke volume is literally the amount of blood that we're pumping out with each beat. So if we take the end diastolic volume, so the amount of blood in the heart at the end of relaxation, and then we take the end systolic blood, so the blood that's left over at the end of contraction, we subtract the fullest point from the lowest point, we have stroke volume, how much blood we pump per beat. Now, if we take that stroke volume and we multiply it by how many beats we've done per minute, that's our heart rate, we're going to get what's known as our cardiac output, and that's the Q with the dot on top of it. Now, one thing that's important for overall health is what's known as ejection fraction. And this is what percentage of blood is the heart able to pump out of itself at rest. And our ejection fraction is going to equal that stroke volume divided by our end diastolic volume. For most people at rest, it's usually around 60%. If you're in a little bit better shape, it's going to be a little bit higher. Individuals that are getting into cardiac failure and otherwise, those numbers are going to be very, very low. So here's just some simple calculations where if the end diastolic volume equals 100 milliliters, the ejection fraction is 60%, and the heart rate is 80 beats per minute, what would the end systolic blood pressure or end systolic volume be? What would the stroke volume be? And what would the cardiac output be? So just for fun, go ahead and throw that up in the chat if you think you know what that would be.
Dr. Lane, could you go back to the previous slide real quick, just for a second?
No worries.
Okay. Thank you. You can go back to.
So really, we're making you guys do a little bit of algebra here.
Dr. Lane, so would the stroke volume be about 60 mils?
Yeah, the stroke volume
Right?
would be 60 milliliters. Because if we've pumped out 60% of the blood in the heart and the end diastolic volume was 100 milliliters, well, 60% of 100 is 60 milliliters. Good job. So what would the cardiac output be?
And systolic will be 40.
And systolic volume would be 40 milliliters because we'd only have 40 left inside of the heart since we managed to pump out the rest.
And then the cardiac output will be 4,800.
Because we're going to take 60 and we're going to multiply that by 80 beats per minute. Exactly.
So it's 4 liters and about close to 5 liters.
Yeah, 4.8 liters.
Right.
Yep. So next up, we've got the vascular system. So we've got here is some ideas for the size of each of these areas. Notice that when we're talking about in diameter in millimeters, our aorta is 25. So we're literally talking 2.5 centimeters, which is the equivalent of almost 1 inch in diameter. Whereas then we go to our arteries, where the larger arteries can be from 1 to 10. And then as we're getting ourselves into our smaller arteries, arterioles, and eventually into those capillaries, we're looking at, they're so small that actually the red blood cells naturally have to fold themselves a little bit to actually get through those segments. And then we're going to go into our capacitance, which is going to be getting into our venules, followed by our veins, and then finally our vena cava. And we're going to see that same thing. They're going to increase the size as we're working up till we get at the largest segment, which is going to be our vena cava, which is literally going to be more than 1 inch in diameter. Now, what's interesting is, since we have a number of valves throughout our circulatory system, is they're going to open and close when we happen to be doing muscular contraction. And we're going to find that this is a good thing, because it's actually going to help with increasing venous return of blood to the heart. So every time our muscles contract, it's actually going to cause a little bit more blood to be pumped back to the heart. And obviously this is going to help with not just aerobic performance, but well, actually that's the key. It really helps with aerobic performance, because it's going to give us a greater amount of preload. Now, our blood distribution is always about matching our demands, which means when we need more blood flow to a certain area via what's known as autoregulation, where we're going to have dilation and constriction. So in general, epinephrine causes vasoconstriction. So we're going to be sending less blood pretty much everywhere in the body, but the local factors are going to cause vasodilation, may it be from carbon dioxide, nitric oxide, or a number of other signaling compounds that are going to be being released by the exercising muscle. So we get vasodilation, which in turn is going to increase the amount of blood flow to those areas. Now, this is thanks to, once again, those controls through both hormonal signaling and paracrine signaling. So at rest, most of our blood is actually in our veins, because those are the capacitance vessels, and they're not having a lot of muscular contraction, which is causing them to be pumped accordingly back throughout the body. I'm not going to insult your intelligence and read these things to you guys, but it is very much so an important thing. When we're talking about blood pressure, this is the general amount of pressure that's being exerted on the arteries as it's traveling through the body. Now, your mean arterial pressure is going to be, mathematically, it's your diastolic blood pressure plus 1/3 of the difference between your systolic blood pressure and your diastolic blood pressure. And we're going to find that when the blood vessels constrict, it's going to increase blood pressure, and dilation is going to decrease blood pressure. We want essentially that dilation to the areas where we want blood flow, and we want constriction to where we don't want it to go, because it's going to do a better job of pushing the blood in only the areas it really needs to be sent to at that given point in time. Now, what we're going to find is cardiovascular exercise is going to increase systolic blood pressure, because the heart is now contracting at a higher intensity, and our diastolic blood pressure is probably not going to change that much. It could go down a little bit, it could come up a little bit, it could stay the exact same, but it doesn't really change that much. It's resistance training that, thanks to the Valsalva maneuver, we're going to have our blood pressure increase massively, as in 480 over 350 millimeters mercury. It's massive. It's the reason why individuals that are very unhealthy, you should be very, very hesitant about them ever performing the Valsalva maneuver, because it literally does massively increase their likelihood of a number of negative cardiovascular outcomes. So, AKA, if you've got bad pipes, you don't want to run really high pressure through them, because you're more likely to rupture one, and an aneurysm is not a good thing. So, here is a graphical representation of that blood pressure when doing aerobic style work. So you can see the percentage of VO2 max, and how that diastolic, stays the same, goes down a little bit. Systolic consistently trends upwards, which then in turn means that our mean arterial pressure is actually going to increase somewhat thanks to that stress. So blood's going to come back to the heart thanks to the muscle pump and the valves that allow it to move effectively one way. We're distributing it through the body based upon its needs, and most of it is going to be going to the active tissue. So right now, when you're sedentary, most of your blood flow is going to your brain, your kidneys, your digestive tract, and your liver. Now, as we go from what you guys are doing, obviously not a lot of physical activity, to higher physical activity, now we're going to see more blood flow is going to our muscles, and specifically the ones we're recruiting. Now, we're going to auto-regulate this through vasodilation, thanks to those local chemical changes, which we're going to get into a little bit more. And we are going to have some extrinsic neurological factors that are going to control blood flow, specifically through vasoconstriction, and we're really talking about mostly epinephrine there. So systolic blood pressure is that highest point during contraction, and diastolic is the lowest point that we're happy to be at, where we start to eject blood from the ventricle. And mean arterial pressure is just the average pressure that's going on in the arterial walls. So let's talk about blood. Most of us got about 4 to 5 liters of it. You can lose half a gallon of it and you're still combat effective. So if you want a fun, weird visual to figure out how much blood you can lose and still be able to hurt somebody and or get away from a situation, take half a gallon of, usually they see you use something like strawberry milk or chocolate milk because it's got some more coloration to it, and pour it on the floor and look how big of a puddle that makes. That's how much blood that can literally be removed from you and you can still fight. So, fun fact, transports gases, nutrients, and removes waste. We talked about before how it's going to help us regulate our pH and regulate our temperature because it's mixing the blood from all the areas of the body. So effectively, it's taking the average temperature once we go to all those different points from our extremities through our core. And that in turn is going to help us also with buffering out those acids that are being produced thanks to doing a lot of anaerobic metabolism. So the vessel walls themselves, notice there's the tunica adventa, media, and interna. Each of those has a different function. The intima is the innermost layer, which we're talking about where we're going to be getting a lot of our distribution. The media is where we're going to find that's effective muscle, smooth muscle that's going to work for dilation and constriction. And then adventica is going to be essentially the fascia wrapping around the exterior of it. Now, inside of our blood, not only do we have red blood cells, we've got our white blood cells, we have platelets, which are going to be important for clotting. And that's where we're going to find our hormones, glucose, and a myriad of other things. So most people, your actual blood is going to be about 55% plasma, meaning it's just water. The other 45% is going to be made up of what's known as formed elements. And 99% of those formed elements are going to be your red blood cells. Less than 1% of that is going to be made up of your white blood cells and your platelets. Now, of that plasma, 90% of it is water. So most of your blood is actually just water. 7% is going to be plasma proteins. It's going to be things like albumin. And then 3% is going to be others. It's going to be things like glucose, all of your different hormones from, insulin and growth hormone are both protein hormones. So they probably count that as plasma protein. So this would be your sex hormones, aldosterone, cortisol, your fatty acids that are going to be floating around, amino acids, and so on. That's going to be part of plasma proteins. Yay. Now, hematocrit is going to be the ratio of their form elements to the total blood volume. So white blood cells are important for our immune system. Red blood cells are important for carrying oxygen and hemoglobin. And platelets are going to be important for coagulation. And so what percentage of our blood is hematocrit is going to give us what percent of it is effectively the formed elements. And it's going to be important for just the general oxygen carrying capacity. For hematocrit's too low, that's when we're going to have situations with anemia. For hematocrit is too high, that's when we're going to have a situation with effectively our blood being too thick and being effectively more likely to coagulate when it shouldn't, which is obviously another thing that's not great for our health. So here is an example where we can go ahead and literally see what's going on with our hematocrit. Notice the very top layer, that's what's known as the buffy coat, and that's what's made up of white blood cells and platelets. The higher part is what's known as the plasma, and that's what's kind of more that yellow tint thanks to the proteins and the other components than just the water that's in it. So we can see an example of B, that someone had a very low hematocrit. So this would be someone that's horribly anemic. And then C, someone has a very high hematocrit, which means their blood is going to be more viscous and is not a good overall thing for them to have for their health. So we're going to find that your cardiac output is going to obviously increase from being at rest to maximal exercise. And what's fascinating is in a relative, so meaning percentage base, your heart is always going to take 5% of its own total cardiac output to keep itself running. Now, what happens is we increase our exercise output from going at rest to that 0 or that 5 liters per minute to that pretty decent intensity of 25 liters a minute. We're going to actually have a higher absolute blood flow. So notice we've gone from 0.25 liters per minute to 1.25 because we're literally going to need more oxygen going to the heart because the heart's doing more work. Now, our digestive tract is going to take a lower relative percentage, but its absolute is actually going to stay the same. If you went even higher intensity, we'd see it go lower. Bone is going to also decrease its relative percentage, but slightly increase its absolute amount of blood flow. It's skeletal muscle that sees a massive uptick in both relative blood flow and absolute blood flow because you're doing more work. Kidneys are going to be going down a lot in the relative sense and a little bit in the absolute. And your brain is actually going to stay about the same, if not go up a little bit in total amount of blood flow. Meanwhile, its absolute amount of blood flow to it is going down. Now, one thing that wasn't covered there was skin, where skin's going to also have an increased amount of blood flow to it. And specifically, as we increase that workload, once we get to the maximal parts, we're going to have lower blood flow to the skin, which is part of the issues with thermoregulation at super high intensities. But we're going to get into that later on in this class. Now, with peripheral blood flow, as we are increasing our workload, we're going to be increasing the amount of blood flow to our periphery. It's a good thing and it's natural because obviously we're having to do greater and greater amounts of work. Now, that viscosity that I alluded to earlier, that is that thickness. And that's going to come down to hematocrit and hydration levels, which is the more viscous, the more resistant to blood flow, and higher viscosities literally mean it's going to be harder to pump your blood. It can get problematic enough to where you can literally have some issues with health. Now, our blood and lymph are there to transport materials to and from our body tissues. Remember, most of blood is going to be made up of plasma, and then the smaller amount is going to be made up of our formed elements. We are going to be binding oxygen to that hemoglobin that's going to be traveling around the body in our red blood cells. And we're going to find that we are going to get an increase in blood viscosity thanks to dehydration otherwise, which is going to increase resistance to flow, which literally makes it harder to send that blood around the body. Now, what's going on with our cardiovascular response to acute exercise? Well, our heart rate's going to go up, our stroke volume is going to go up, and in turn, our cardiac output is going to go up. Blood flow is going to increase and blood pressure is going to change. Remember, mostly the changes with aerobic training is going to be in the systolic blood flow. And this in turn is going to allow us to exercise at a much higher intensity. So if you look at the image in the bottom right, those are cross-country skiers, and some of the highest VO2 maxes in recorded history have all been in cross-country skiers because it is such a total body aerobic stressor. Now, resting heart rate is going to depend on your level of physical fitness. Most people at 60 to 80 beats per minute. It can go as low as into the 20s for people that are in incredible aerobic shape, and it can be all the way over 100 beats per minute for individuals that, could be the heart transplant case or individuals that are just not as physically fit. And it tends to go down as we get older and with being in better shape. Now, environmental conditions such as being in altitude is going to increase our heart rate because we're not getting as much oxygen saturation. So we literally have to pump more blood around the body to keep ourselves in homeostasis. And if we happen to be in very hot environments, and because of the increased cardiovascular demand to the skin, specifically so that we can sweat it out to help thermoregulate, that in turn is also going to elevate your resting heart rate. So max heart rate is literally—
I have a question, Dr. Lane.
Go ahead. What was that, Ihor?
I have a question. So with altitude, exercising at altitude, wouldn't your the effect of erythropoietin increase and you'll create more red blood cells, and then wouldn't that level off the heart rate in a sense? Would that affect the heart rate? Or after time of you exercising at high altitude, would you match? Will your heart rate will it go back to normal after a while because of more red blood cells created? Is that how it works?
So the key is we all have a limited ability to adapt to stressors. So your idea there is right in the sense of over a long enough period of time, like if you go from living here to living in like Colorado Springs, you go to living in like Park City, Utah, a place where you're at altitude, but you're not at like a vicious altitude, your body will adapt and increase your hematocrit to a certain extent. But once again, we all only have a limited amount of adaptive potential to whatever stressors we happen to be applying to the body. So if you wouldn't just adapt to living at Everest, the partial pressure of oxygen is low enough because of that altitude up there that there's no amount of adaptation that your body is going to be able to maintain for an incredibly long period of time that's going to sustain your health and performance. Now, you are going to get better at it, and you are going to be able to maintain effectively a higher level of functionality than you would have without doing any adaptation to altitude. But unfortunately, there's a limited capacity there. So yes, it's going to take a couple of weeks to fully acclimate to being in altitude, but you're not going to be effectively as well adapted as one would hope. Like, you're not just going to be able to live up there. And I'm referring to like crazy altitudes. Like, we're talking over 10,000, over 15,000 feet. Yeah. Now, your maximum heart rate is just the highest heart rate that you can get in an all-out exercise, which is really like pushing the brink of exhaustion, meaning you're done, son. You're not going to be able to keep that up. Now, it tends to be relatively consistent from day to day, but it's going to change from year to year, where it typically is going to go down a little bit. And it goes down actually a little bit whenever you get to be in really, really good aerobic shape, just because your heart is bigger and it's just a larger heart. It takes longer to completely contract and relax each time. So hence why you guys have probably seen the 220 minus your age formula, which is great when you're working with young kids. Now, it's still going to have an error variance of plus or minus maybe as much as 10%. So it's not perfect there. And then where there are variations on these same formulas depending on the individuals you're working with. So if you're dealing with a female that's over 35, we take that 206, multiply their age by 88, and then subtract that from that 206 to get their estimated heart rate max. So we're not expecting that full beat lost every single year. And especially once we get older, with older adults, we're talking in the 50s and 60s plus, then we're going to use that 211 minus 64% of their age. So your heart rate tends to match your intensity pretty linearly. So the heart rate goes up in accordance with how hard you're working. If you're not working that hard, the heart rate's not going to go up that high. However, that's why we care about things known as steady state heart rate, which is getting you to work at a given speed on a treadmill, on a bike, etc. That is going to let us know effectively how hard that is for you cardiovascularly. Because your body, after enough time, is going to adapt to it and effectively pump at the optimal rate it needs to in order to maintain that work output. So if we're able to maintain a lower steady state output at a given workload than we did initially, that lets us know that we are now in better shape, that our heart is more efficient. That means our stroke volume's gone up, or we're requiring lower metabolic demands to do the same amount of work because we become more mechanically efficient or more metabolically efficient. The racehorses are down there because racehorses are interesting because they're natural blood dopers. They have a contractile spleen, so when they need extra blood cells, they can literally contract it, which is going to drop them into the bloodstream and allow them to perform on a higher level than one would suspect. Now, stroke volume itself is a big part of what we're able to do. Now, what's interesting is stroke volume, it maxes out at only about 40 to 60% of our actual heart rate max. For some folks, it might not max out until you get to about 80 or 90. But this is literally allowing us to pump more blood per beat. And depending on our body position, meaning if you happen to be in more of a horizontal position, like swimming, it's much easier for your heart to pump more blood per beat because it doesn't have to overcome gravity, as opposed to when you're upright, when you're doing something like running, where you have to not just pump that blood out of the heart and overcome the pressure of the aorta, but you also the heart has to literally lift itself up in the process of contracting, which requires, obviously, energy in and of itself. So most of your athletes are going to be hitting that stroke volume maximum somewhere in that 40 to 60% of their max. And this is a good thing because this is why submaximal exercise is a great thing for the heart, specifically when we're talking about the aerobic effects, because we don't have to go all the way up to 80, 90, 100% of your heart rate max for individuals that are even moderately trained. We only have to get up to 40 to 60% of our heart rate max, and that's going to do some good work on helping us enhance our stroke volume. So in turn, we're going to be able to pump more blood per beat, which is, once again, going to help the heart not just deliver nutrients throughout the body, but make the heart healthier in and of itself. So what we're going to see is individuals that happen to be in better shape are literally going to have much greater stroke volumes. So here's an example specifically from cyclists as they worked up higher and higher into percentages, or into essentially their heart rate max. The individuals that were very well trained were still seeing those the stroke volumes increase all the way up to effectively their max. And once you get to the max, because the heart doesn't have as much time to refill between each contraction, you naturally have a slight decrease in efficiency of the heart and hence a slight decrease in stroke volume. But these are the ends of the spectrum from people that are physically fit, and few people are going to be all the way up there. Now, what we're going to see is our stroke volume is going to increase to a certain extent, and this through a myriad of ways. One is what's known as the Frank-Starling mechanism, which is we're going to have more blood filling in the ventricle thanks to that preload from the mechanical return through the valves in the veins, which is going to cause the heart to stretch more. So we get better optimal cross-bridging of actin and myosin, and this in turn is going to cause it to contract with more force. Now, this increased ventricular contractility, which is also going to occur thanks to epinephrine, is going to cause, once again, more force. And we're going to have lower total peripheral resistance thanks to vasodilation from the metabolic demands of the exercise. So we're going to have less pressure we have to overcome on the other side, specifically vasodilation to the blood vessels that need the blood flow, aka going to those active muscles. So with those combined, we are able to really massively uptick our cardiac output and specifically our blood flow to the regions that specifically need it. So as we happen to be increasing our exercise intensity, we increase that contractility, and we're going to increase our end diastolic volume. So we're going to be able to fill the blood more fully with, or fill the heart with more fully with blood. So it's going to be able to literally pump that much harder with each individual beat. So as we're working up in exercise, you guys can see that end diastolic volume and the end systolic volume. And so the difference between someone doing supine, so laying down exercise, as opposed to doing upright exercise, you see how we get a greater difference between the two with that stroke volume when we happen to be laying down as opposed to standing. And that's again, to that gravity effects. Sorry, somebody's whistling very loudly in the hallway. So at rest, our cardiac output is usually about 5 liters per minute, plus or minus a little bit depending on body size. We're really just cycling through all the blood in the body once per minute. And this is going to increase with exercise intensity to about 20 to maybe 40 liters per minute for really, really in good aerobic shape. Now, this is going to increase depending on your body size and your endurance total amount of conditioning. So I'd be very fascinated to see what the total cardiac output would be of some guy like Hafthor Thorson, just because he's a massive human being, compared to, you know, really elite level marathoners. He might actually have a higher cardiac output than they do, but the key is he is so much bigger that there's a reason why he's not has a chance at anything of keeping up with them with doing things like marathon running. So once we peak out that stroke volume in that usually that 40 to 60% range, any additional improvement in cardiac output is only coming from heart rate. And that's important because we're going to use that whenever we're trying to come up with estimations of maximal or VO2 max through submaximal tests, thanks to looking at how that cardiac output is going to be trending. So what we have here is that same basic idea of how our cardiac output is going to keep increasing until we hit a point where it doesn't increase anymore, which is also going to be coinciding with that VO2 max. We can technically run faster than that. That's what sprinting is about, but you're not able to support that work aerobically any further. So as we're going from laying down to standing up and getting after it, our heart rate's going to increase. Stroke volume actually initially decreases when you go from laying down to standing up, because now we have to deal with gravity. However, at the same time, we're going to see a greater increase in stroke volume from what it was when we were laying down once we started exercising. And so our overall cardiac output when we're laying down and standing up is relatively similar because we don't have a lot of metabolic demands. It really increases when we start exercising. So, you guys okay? You guys still with me? Sounds good. So this is just kind of giving you guys some more numbers to kind of think about as far as when we're talking about resting, laying down, standing, or sitting, to then going ahead and working our way into higher and higher exercise intensities of the cardiac outputs. If whether we're maximal running, cycling, or swimming, are all going to be pretty high. It just depends on what the body's capable in those positions. But this is the graph that I think is very important for you to understand, which is this is going to be looking at that blood flow to the different tissues of the body when we're looking at them as percentage of total cardiac output. So we can see as we go from being at rest all the way up to maximal exercise, we initially have an increase in blood flow to the skin, which literally makes us thermoregulate better when we're doing light exercise. But then once we get up to heavy, it's still better than we were at rest, but it's not as good as it was when we were at light. But when we're at maximal, we're sending so much blood to the muscles. You can see how that blue bar just keeps getting more and more massive. We literally aren't able to get enough blood flow to our skin to really help support our ability to sweat like we really need to. We're gonna have less and less blood flow in general, obviously, to both the kidney and to the brain. In the relative sense, absolute is gonna stay about the same for the brain, go down a bit for renal, but nothing too bad like we talked about earlier. And notice that effectively I'll call it the forest green bar. For the heart, it stays the same the entire time. The heart takes its cut of that 4 to 5% of cardiac output, irregardless of what intensity you happen to be exercising at. So now look at this in the actual absolute. So we see how that cardiac output goes up and up and up as we increase our exercise intensity. So you can see how you actually peak out the blood flow of the skin in heavy exercise, but then it decreases when you go to maximal. Once again, there's your issue with thermoregulation. When we increase our blood flow, the big thing that is going to get more and more is always going to be muscle. And we can see how the brain stays relatively consistent with that gray bar on the very bottom. Meanwhile, the heart, that green bar, the forest green one, is going to increase consistently. So understanding how the cardiac output is going to change based upon the demands that happen to be going on with the body. Now, once you've been exercising for a long enough period of time, thanks to the fluid loss from sweating and then moving into other compartments of the body, we are going to undergo what's known as cardiovascular drift, which means literally, because we're not getting as much stroke volume as we did before because of the change in total peripheral resistance and then essentially the viscosity of the blood, we are going to have to increase our heart rate to maintain the same output. And this is what's known as a cardiovascular drift. Now, this is important because this is going to be one of the factors that's going to also help lead to fatigue whenever you happen to be doing very long periods of aerobic style training. Now, how our circulatory system is going to respond to the exercise that we're doing is probably what you guys would think, and that our heart rate's going to go up, which in turn, from the cardiac drift, our cardiac output is going to stay about the same because notice, guys, the blood volume goes down a little bit, but our arterial pressure goes down, our pulmonary arterial pressure is going down, and our stroke volume, most importantly, is going down with time. And so this eventually is going to be a contributing factor to fatigue. So exercise intensity goes up, heart rate, stroke volume, and cardiac output are also going to go up. We are trying to send that blood around the body to whatever level we need to, specifically to the areas that we need them to go to through vasodilation to those areas of vasoconstriction everywhere else. And we're going to find that as we keep sweating it out, we're going to have cardiovascular drift, which gives us lower stroke volume, so we have to make up for it with a higher amount of heart rate. Now, our systolic blood pressure is going to increase pretty much directly with the amount of exercise intensity. Diastolic is going to stay about the same, and we're going to massively increase that blood pressure when we happen to be doing a Valsalva maneuver. So bearing down has its liabilities if we're talking about unhealthy people. Not worried about Valsalva maneuvers in people that are healthy, other than if they're not careful, they can black out, which makes for, unfortunately, videos on the internet very much so at other people's expense. Now, the AVO2 difference, arterial venous oxygen difference, is literally how much oxygen is being extracted when blood goes through the capillaries, so from the arterioles into the venules. So we're really looking at how much oxygen was in it when it was in the arterioles and how much oxygen is in it when it gets to the venules. And this difference shows a greater ability of those tissues to take up oxygen. Now, we're going to find as we're increasing exercise intensity, we're going to also see a greater AVO2 difference because we're doing a better job of sending blood to those areas. And when that blood gets there, those tissues are going to do a much better job of pulling the oxygen from it as it happens to be passing by it. Now, what we're going to see also when we're exercising is we're going to be decreasing our plasma volume. Part of that is because it goes into our interstitial fluid, meaning it's going to be effectively outside of the bloodstream and into effectively the areas around our cells. Now, we're going to be losing a certain amount of it thanks to the joys of sweating, and excessive fluid loss is going to cause a decline in performance. That's going back to the cardiovascular drift, and is going to cause hemoconcentration, which is going to make our heart work harder because, once again, our blood happens to be more viscous than it was just previously. So AV2O difference is going to become greater as we're exercising. So we're doing a better job of pulling oxygen from the blood. We're going to see that plasma volume decrease thanks to going to interstitial fluid, and because we're sweating it out, we're going to in turn have hemoconcentration. So because of that, we're literally going to be able to actually carry more oxygen in the blood per unit. However, because of that increased viscosity and the resistance to blood flow, it's going to cause a decrease in overall performance. And we're typically going to have a decrease in our pH because of the accumulation of lactate and the wonderful proton that comes with it when we get up to higher exercise intensities. And that's going to come down to the blood lactate threshold, which we're going to get into in a bit. So what can we tell you? With endurance training, you have to understand there's two separate things. Muscular endurance is your ability to do a repeated effort with a muscle itself or a muscle group. So an example of this would be doing something like a maximal pull-ups or maximal sit-ups in a minute or 2 minutes. Now, cardiorespiratory endurance is your body's ability to maintain a prolonged steady state exercise. So this is going to be running, cycling, swimming, etc. And this is important in regards to it's a good overall test of your cardiovascular system and your respiratory system. So literally, your ability to breathe, which is obviously being tested by a number of people right now where they're realizing that they're in not good shape because even wearing a little piece of cloth is enough for them to be all whiny and talk about how they can't breathe. If that's all it takes is a thin piece of cotton and that's choking you out, you be soft. And it's okay to be soft. Just own it, Now, our greatest ability to utilize oxygen during exercise is what's known as the VO2 max. Now, the VO2 max is going to be something that can increase through training. There's a major genetic component to both where your baseline level is and how adaptive you are, along with it's also relative to your body size. That's why your highest level aerobic athletes typically are not very large people. And our submax endurance capacity is going to be really important because that's going to be what performance level we can keep up for very long periods of time. So aerobic athletes, and specifically it's going to be the fraction, thanks to the lactate threshold, of your VO2 max that you can maintain for a longer period of time. And this is a much more difficult thing to measure because it requires us tracking a number of values, our ventilatory threshold, our lactate threshold, and looking at things like effective movement efficiency. And same thing, this will increase with training. So you can see as much of you can see as much of a 50% increase in VO2 max in training, and typically you're going to be able to max out most people's VO2 max as far as really get those improvements in about 1.5 years of training. Now, this is all going to be influenced by obviously the size of your heart, how much blood you pump per beat, what's that maximal heart rate that you're going to have, which in turn is going to influence your cardiac output. Blood flow is going to be important when we talk about the vasodilation and vasoconstriction appropriately throughout the body, how our blood pressure is going to respond to allowing those flows to occur, and then just the general overall amount of blood flow. All of these tend to improve in their own way thanks to training, and that's a good thing. Because the fun thing about aerobic style training is no matter what methodology you use for aerobic training, you tend to be a healthier and effectively, have better longevity outcomes, irregardless of whatever aerobic style of training you like to use. May it be your aerobic style of training is running, dancing, pogo sticking, or hula hooping. If you do anything with enough intensity aerobically, you're actually going to help enhance the functioning of your cardiovascular and your pulmonary system to a lesser extent. So, how much oxygen we're going to be sending to the area is going to come down to what's known as the Fick equation. So this total volume of oxygen is going to equal our stroke volume multiplied by our heart rate multiplied by the AVO2 difference. So this is our cardiac output multiplied by our AVO2 difference. Remember, the AVO2 difference is how much oxygen was in the blood when it was in the arteries, and now how much oxygen is in the blood now that we're in the veins. The bigger that difference, and then obviously the higher the stroke volume, higher the heart rate, the greater amount of oxygen that we're able to send into those areas, which is going to allow us to perform on a higher level. So what's fascinating is when you compare a normal person to an athlete, athletes that happen to be doing aerobic work tend to have a greater or greater numbers in the number of spots of their heart's health and otherwise. So left ventricular internal dimension, so that's literally how much space your heart has inside. It helps with the capacitance. Interventricular septum thickness, that's IVST. So that's effectively how thick is the wall. And yeah, it's a little bit thicker, but notice the difference isn't as severe as opposed to was that internal dimension. That is the left ventricular mass is LVM. So it's literally how much muscle mass is in your heart. Notice the cyclists were the highest. And then the posterior wall thickness, same thing. It is going to adapt and it's going to be higher in our aerobic athletes as opposed to our anaerobic. And so if you're trying to look at just general overall difference, and so yeah, mean wall thickness is going to be the one in the center. Your cyclists actually seem to have the greatest amount of cardiovascular adaptations to your endurance athletes, and then way better than your strength athletes. The reason why your endurance athletes are not as good is going to be for the fact of compared to your cyclists is because remember, your long distance runners have to overcome the effects of gravity. Whereas your cyclists, they don't have to overcome the effects of gravity. They don't have to worry about body weight relative performance because it's more about just total wattage output and then wattage relative body mass, but they're not really in that efficiency game with a long distance athlete. I probably just said that in a way that makes no freaking sense. So Yehor or Jabari, try to say what I just said in whatever makes sense to you, and I'm going to clarify it.
So you wanted to say, to interpret what you said about cyclists, how, is that what you said?
Yeah.
Okay.
Why would cyclist hearts be arguably even better aerobically adapted than long distance runners?
Gravity is not affecting them. That's what I got from.
Good, Jabari. So one way to think about it is effectively your long distance runners are effectively like trying to make a car, but trying to make that car as light as possible. So you're literally trying to take apart, get rid of the extra seats, get rid of the upholstery, get rid of the freaking doors if you can. Try to make that thing literally an engine with a steering wheel and wheels. Like you're trying to make it as light as possible. Whereas when you think about a cyclist, because we don't have to deal with all those impacts that we naturally get with running, we are now focusing on having the biggest engine we can have because we don't have to deal with those extra stressors. Does that make sense?
Total, yeah.
Okay, cool. Like I said, it can be kind of a harder thing to conceptualize. So it's the reason why you can see cyclists that have got like some massive legs, but you never see long distance runners that you're like, damn, that dude is jacked. If anything, you're like, damn, that guy is fast and he should eat more. But the funny thing is they usually eat huge amounts. So the left ventricle is the one that changes the most thanks to endurance training. The internal dimension, aka how much blood we're going to be able to fill with and pump out, is going to really be what's increasing the most. And the thickness of the wall is also going to increase because we're literally going to be able to contract with more force, which is going to increase that ejection fraction, which in turn is going to enhance our total stroke volume and in turn our aerobic performance. So as you guys would suspect, you go through longer periods of training, your stroke volume is going to go up higher and higher. The fun thing is individuals that happen to be in great shape compared to people that are sedentary are naturally going to have a higher stroke volume than the rest, and then they're going to have a much higher stroke volume at maximal exercise. So it's 7 o'clock. I promise you guys we're only going to do this for an hour because you guys know the lab is exciting and has a lot of things going on. Plus we covered a lot of material in a relatively short period of time. Are there any questions you guys would like me to go through? And I genuinely appreciate you gentlemen showing up to lecture because otherwise it's me talking to myself and I don't like doing that.
Question, but it's not related to cardiovascular and that we're going through. I have a question actually about the quiz and just the sequence of steps of muscle contraction, skeletal muscle contraction. Because I think when I was answering that question in our homework quiz, I got the order mixed up somehow because I thought. Anyway, if you could go through that again, just like the order of steps, not in like super detailed, but as it was in quiz.
Yeah, no worries, bud. Okay, so remember, that effectively it's going to start off by the action potential is going down the motor unit until we get to the axon terminal. Once it gets there, it's going to cause a vesicle with acetylcholine to be released from the end. Or vesicles is more than one. That acetylcholine is going to go across the neuromuscular junction. It is then going to bind to the ligand-gated receptor. When it binds that ligand-gated receptor, it's going to allow sodium to influx into that muscle cell. Once enough sodium goes into the cell, it's going to increase the voltage from about, typically -70 or so to about -50. When it hits -50, that's when what's known as the voltage-gated channels open, and we have an action potential. So that's going to open one channel, which is going to cause the channel next to it to open, which is going to cause the channel next to it open, and it keeps going from the neuromuscular junction down the sarcolemma and then down the T tubules. When it goes down the T tubules, it's going to go through the DHP and ryanodine receptors, which is going to cause that same action potential now to cause calcium to be released from calsequestrin inside of the sarcoplasm. When this occurs, this calcium is going to go into the sarcoplasm. When it's in the sarcoplasm, it's going to float over and bind to troponin C, which in turn, through troponin I, is in turn going to grab with troponin T and move tropomyosin off of the binding sites of actin. Once the binding sites of actin are exposed, myosin is going to grab hold of actin. At that point, ATP it's going to grab, and then it's going to ratchet forward. ATP is going to go ahead and go inside that cleft, which is going to cause it to release. It's going to hydrolyze, which is going to cause it to spring back, and then it's going to grab again if it can, and it's going to keep going and doing so as long as those binding sites of actin are exposed and that calcium is still binding, or then ATP is available. Now, once action potentials are no longer being sent, in turn, the calcium ATPase pump is going to be pumping calcium back into the sarcoplastic reticulum. And when that occurs, that calcium is going to go back in there and is going to bind to calsequestrin again, and the muscle is going to relax.
No, I see like that wrong.
I think that was a lot of steps.
Guys, it's a lot. It's a lot. And I don't ever want to lie to you and say it's not. But the key is understanding the mechanisms of how muscle functions. It's one of the major underpinnings of exercise physiology. So this is one of those, the only way out is through type situations. So are there any other questions that I can answer for you guys?
The equation you gave in the beginning of class, I just wanted to make sure, you said 4,800 Q for the heart rate and the, I forgot the other term.
Stroke volume. Yep.
Yeah, stroke volume.
Output is going to equal that heart rate multiplied by that stroke volume.
And the ESV, would that be -40?
Okay, so the end systolic volume, it would be 40. Does that make sense?
Oh, it's not negative. It's just. No,
because think about it. That would somehow be negative. There would be negative blood in the heart at the end of.
Got you. Okay.
Yeah.
So
no matter, no, dude, you're learning. At the worst case scenario, the end systolic volume is always going to it's going to be a positive number. The key is the smaller that number is relative to the end diastolic volume. So how much blood was in the heart at the end of relaxation, that's going to let us know how much blood got pumped and then how good the ejection fraction is. So you want a higher ejection fraction and you want a higher stroke volume. That's a healthier heart.
Higher ejection fraction?
Yes. It means you're doing a better job of pumping all the blood out of the heart with each beat.
I have another question. About that second lab, do we, when we make our presentation, and we analyze our data, what exactly would you want us to put as far as this topic that we're talking about right now? Is there anything you want to calculate as far as that goes?
No, it's okay, bud. So the basic idea with this lab that you guys are going to go ahead and finish out the data for and you're going to present on is I want you guys to go ahead and look at and explain effectively, how do load carriage influence changes in, could be VO2, could be on RER, could be on the heart rate itself.
Okay, I got it. Okay.
On, you know, and obviously you guys can bring up the changes in body weight that occurred. You've got a lot of different variables you guys can look at. The key is each of you are going to pick your own, and this is another thing which it's just a t-test. You just look at pre-post changes.
So we just choose one that we really want to score and record that.
Yes, you're just looking at the one or two variables, Sihor. Now, your connection is a little scratchy, so I'm kind of guessing on the things you're saying a bit, bud. And the key is, you know, that's why I'll see you guys in the lab again probably tomorrow, so we can obviously talk about this in person. But figure, you know, that's why we're going to get all this data initially. It's important that we enter it in appropriately, and then you're trying to look at, you know, effectively what the differences is. And so you can break it down then by individual stage, which is kind of an uglier way of doing it. It should be technically what's known as an analysis of variance. We should probably be doing like a 2x3 or 2x4 analysis. But if I just said that, it makes absolutely no sense to you. That's okay. That's the thing. You guys are learning. And so that's why we're going to sit down and talk about this more in person. And kind of that way you guys can kind of see it imaged.
Eeyore, what time are you going to the lab tomorrow?
I'll be there at 9.
All right.
So, and I'll be there before you guys are done testing for sure. Biomechanics has their first, hold up, I'm gonna stop recording.